very good morning. Myself Veena Gowde, Assistant Professor from Electronics and Telecommunication Department, AP Shah Institute of Technology, gives a warm welcome to all participants and guest speakers for the second day of AICT ATAL sponsored Faculty Development Program on IoT, a journey from sensor to server. Yesterday, Dr. Kaushik Guha shared valuable knowledge about energy harvesting and powering up the sensors in IoT nodes. Now, let us resume this learning journey of IoT with the first speaker of the day. On behalf of AP Shah Institute of Technology, I take this privilege to introduce Dr. Ninad Mahendri. Dr. Ninad Mahendri is a postdoctorate from KIT Germany and holds a PhD degree in microfabrication and image processing from the Indian Institute of Technology, Bombay. Currently working as an associate professor in the electronics department at KG Somaiya College of Engineering. He was working as a scientist with the Institute of Microstructure Technology at Karlsruhe Institute of Technology, Germany for 1 year. During this period, he developed a real-time microfluidic bioreactor with NMR measurement capabilities. He also developed a machine learning algorithm to classify FTIR signals obtained during waste to biofuel production process. He was gold medalist during his MTech at NMIMS University. Dr. Ninad is the founder and was chief researcher for 11 years at Ninad's research lab at Thane. He made more than 1,900 projects in various domains ranging from computer programming to robotics. Ninad sir is currently consulting many industries such as STMI, Europe, Xenium Digital, that is India, and Lvdt Center of Excellence, India. Also, Dr. Mahendri is consulting many academic institutions like Vidyalankar Institute of Technology, SBMP, Prerna Group of Institutions, and Kohinoor Technical Institute. His core areas of expertise are signal processing, machine vision, embedded systems, microfluidics, microfabrication, MEMS, NMR, bioprocessing of waste, robotics, deep learning, AR/VR technology, and many more. So, I would like to invite Dr. Ninad sir to give a talk on the topic of selection of sensors. Over to you, sir.
Yeah, thank you. I hope am I audible?
Yes,
thank you
sir,
for
you're
this
audible.
overwhelming introduction. So I'll start my screen share. I hope it is visible to you all.
Yes, sir, screen is visible.
Thank you. So as you all know that today's technology is sensor driven, and based on the domain of IoT, nothing can be worked out without the sensors. Internet of Things actually start with the data which is collected by the sensors. Now we know about human sensors like vision, hearing, smell, taste, and touch. Now its equivalent sensors are also available in the electronics domain, or what you can say machine can also do all this stuff. And it's pretty interesting to know how these sensors are achieved using different kind of technology that are MEMS technologies that are coming up nowadays. Now, sensor is anything that produces a signal relating to physical quantity being measured. So a very short definition of a sensor. Now, people do get confused between sensor, transducer, sensor module. There are different types. So basically just remember a sensor is a thing that converts a physical quantity into some measurable signal. That's it. So just forget about all other confusing terms. Now we see our day-to-day instances for the sensors. When you stand in front of a mall, the doors automatically open. So there is a sensor that we discuss about that micro sensor, which is used to do all the stuff. Then we put our hand in the lift and lift stops and door automatically opens again. So there is a IR sensor used in this kind of mechanism plus a pressure sensor. We also see a lot of smoke detectors installed everywhere, especially in the premises, office premises, to detect a fire. So fire alarm based sensors are already installed. So these are the day-to-day instances of the sensor. Now, sensors in industry, there are a lot of sensors popular for measuring boiler temperature, boiler pressure. So there is a temperature sensor, there is a flow measurement sensor, pressure gauge, level sensor. So these are the four very common sensors used in industry. And just to give you a rough idea, these temperature sensors can measure up to thousands of degrees without getting burnt. So this is where a transmission of temperature happens, and that's where it could able to measure such a high temperature. Now, many DIY projects also need sensors, and students are making a lot of these sensor based project. Like this guy over is made a weird system that can measure a count of your push-ups. I don't know what is the use, but there are many such projects coming up, and there is a gas leak detector. So this is a sensor, and the circuit below is what we call a signal conditioning unit. And most of these sensors do require only 5-volt ground and one analog output that typically goes to the microcontroller circuit. Currently, whatever they have shown, it's called microcontroller Arduino Uno. And this is where sensor module comes into the picture. So a sensor with signal conditioning and a power supply, everything consists of a sensor module. Now, most of the times when we talk about sensor, these are the modules and not the raw sensor. Now, things to consider before selection of sensors. So when we come to the selection of sensor, which is today's topic, the first thing is intended application. So this is the only thing which I would prefer, that whether it's a household application, whether it's an industrial application, whether it's a IoT sensor, etc., etc. Now, output type, whether you want an analog output or digital output, so that you have to consider, because if you have an analog output, you need to further convert it using ADC, and your entire sensor range is now controlled by the resolution of that ADC. Then current and voltage requirements. So many of the times people forget that there is certain amount of current required to draw the sensor. People just connect 5 LDRs in parallel like this, and they don't even consider that if the current drawn by one LDR is higher, the other LDR's reading might get affected, because at the end of the day, it's all voltage division. So if you change the current flowing through one branch, your output voltage is going to get hampered. So you are not supposed to connect the sensors in parallel. Typically, I would suggest always use a separate supply for each sensor, and you just make their ground common. So you are not supposed to divide your voltage supply. Typically use a separate regulator for each sensor. You can use a common battery. I'm not saying use different battery. Ideally, yes, if you use different battery, that will be even better. But at least use a separate regulator for each sensor. Coming to the response time, you see that most of the sensors do respond in milliseconds, and our human, whatever activity we do, we generally don't work in milliseconds. We do all the activities in seconds. So there could be some sensors that respond after a second. There could be some sensors that respond after minutes of their measurement. Now, I will talk about these sensors later on, why they are so slow, and it doesn't matter even if you measure after few minutes. Now, next is environment. So external environment where you are going to put this, it could be extreme temperature, could be some chemical which will erode the sensor outer shielding, etc. Or it could be hazardous environment where a single spark can turn on the fire. Then range. So there are short range sensors and long range sensors. Typically, short range sensors are, let's say, only 0 to 10 degree. Okay, but they have a lot of resolution, like it can measure in terms of 0.001 degree Celsius. So these are the short range sensors where the resolution is high. And then there are long range sensor which might measure from 0 to 1000 degree with accuracy of 1 degree. So compared to this, resolution is way less than this range. So both kind of sensors are required depending upon the application. And output devices, generally it depends on what kind of output that you use. Actuators are used or not, so that the response time can be controlled, and based on that your sensor selection can happen. Now, resolution. Let us try to define what are the sensor terminologies And those who are totally unaware of this particular sensor terminology, let us go into the detail of one by one term. I know many of you might have taken the subject of instrumentation, where they do explain all these terms. So first is resolution. Now, we generally go to buy a TV, we say 4K resolution. Okay. Now 4K, 8K are all what you can say number of pixels that you can see on that small screen. Okay. So if you are using a 32-inch TV with 4K resolution, it will have more pixels than, let's say, 80-inch TV with 4K resolution, because the size is bigger. So smaller the screen size and more the resolution, more number of pixels you can fit. So ideal resolution is more. Okay. Now in 80-inch 4K resolution, what you say 4K is basically number of pixels. Okay. So it's the smallest detectable incremental change. Okay, that is what we call the resolution of the input parameter. Okay, let's say it is a temperature sensor and it can measure up to 0.01 degree Celsius change. Then the resolution of that sensor is called 0.01 degree Celsius. And smaller the resolution, better the sensor is. Not always, because let's say if you are measuring a room temperature, you can just go away with 27 degrees. You don't want 27.01 hai at 27.002 hai. Okay, it doesn't make a lot of difference to you. Okay, so sometimes the resolution is not required. Higher resolution sensors are costlier, so you don't always go for higher resolution sensors. So my suggestion is always that choose a sensor which is good enough for your application. You don't have to choose the highest resolution sensor every time, because remember, it will come with its own cost, and based on the microcontroller storage, this kind of resolution will take more memory, so it will again slow down the system. So it is very important to choose a sensor with a appropriate resolution. I will not say go for highest resolution. Again, this is quite a contradictory statement, as I earlier said that higher the resolution, better is the sensor, but you should always choose a sensor with your appropriate resolution requirement. Next is precision. Now precision is degree of reproducibility of the measurement. Okay, let's say you have one room, you put one sensor, you take the reading, you got, let's say, 27 degrees Celsius. Okay, now again in the same room I put the same sensor, and this time I got 26.9 degree. So you will say it's not much variation, but as per the precision goes, it is not precise sensor. So precise sensor should always give you 27 degree for the same room, provided the actual temperature is not changing. But this is how a precise sensor should work. So ideally, the sensor has to be precise. Every time you take the same measurement, you should get the same results. Again, higher precision sensors are costlier. So if you are okay with this fluctuation from 27 to 26.9, you can go for a lower precision sensor. Again, you see that sometimes the precision sensors are what you can say within some margin of error. We typically select 5% precision. So if your next reading is within 5%, you just let this sensor as a good sensor. Okay. Next is range. So range is the maximum and the minimum value of the applied parameter that can be measured. This is the most important factor to consider. You forget about the reproducibility of the reading, you forget about the actual resolution, but range is what you should always consider. Let's say you are putting a sensor for a boiler that goes up to 800 degrees Celsius. Okay. And then you put a sensor that can measure up to 125 degrees Celsius. So what will happen is this sensor will melt down as soon as you install this sensor. So range is always important parameter, and this is the only parameter you should always consider. This is what we can say priority number one. What is the range? Now, if you want to measure 800 degrees Celsius, at least 20% more range, let's say 800 into 1.2, that much range sensor you should choose for this application. So this is a maximum. Similarly, there could be a minimum value. So let's say it could be for a freezer with minus 40 degree measurement range, and you try to put something which can measure from 0 degree. So what will happen is the sensor will froze itself and it will not work. So that's why it is very important that you put a sensor with correct reading or range. So throughout this talk, I will be only talking about the range. Yes, we can go in detail for each and every sensor's resolution or precision, but that will take a lot of time, and then within 2 hours, it is not possible to cover all the content. Next is sensitivity. Sensitivity. Now, this is very important term. This is the input parameter change required to produce the standard output change. Let's say I want to create a 1 volt change at the output. What is the input parameter change I should do? That will define a sensitivity. Okay. So if I change the temperature by 10 degrees Celsius, then the output is producing 1 volt of change. Then I can say this is a sensitivity of sensor 1. For another sensor, let's say if I change the temperature by 1 degree and output is changing by 1 volt, then this is a second sensitivity of the sensor 2. Now you will see that this sensor is more sensitive compared to this sensor. Okay. So lower this number is, better is the sensor. So sensitivity should be as high as possible. Now, when I say sensitivity should be as high as possible means only 1 degree of change in the input is creating a 1 volt of output change. And that's why this is having higher sensitivity. So it's kind of non-intuitive that your number is smaller and then we call the sensor is more sensitive. Okay. Next is accuracy. So accuracy is maximum difference that will exist between the actual value which is to be measured and the indicated value at the output of your sensor. So obviously we don't want inaccurate sensors, but we can live up with 99% or 98% accurate sensors also. So again, accuracy is a parameter which is very important for a sensor, and you should ideally have a 100% accuracy sensor. But because of some, you can say, cost factors, you can choose a sensor with a slightly lower accuracy, and that could save you a lot of money. Okay. So let's say 100% accurate sensor is costing you 1,000 euros. Then maybe your 98% accuracy is costing you €1. So you should always go for 98% accuracy sensor. So see, just adding 2% of accuracy is not gonna make a very much difference to the actual sensor output. So why to go for 100% accuracy? You can always. So it's a game of cost versus accuracy, and this is a exponential growth of cost. So once till 95, it's okay, but after that cost goes like exponentially high, and let's say at 100%, it almost becomes 10 times the actual cost of whatever you have at 95. So that's why it's very important to choose a accurate sensor within certain limit. Now you will say this throughout this discussion, I am just telling that don't go for the best one. The only reason is the firstly I told it's the cost. Okay. Secondly, the since your IoT devices are the edge computers, okay, they will not have a lot of memory, and there is a lot of junk data getting produced. For example, I will give you an example where you have your room temperature of 27 degree. Okay. Let's say if you measure this temperature every 1 second, there is not going to be much change. Okay. But if you upload this data over internet, so a lot of bandwidth getting wasted, just you're uploading same number every time. Okay. Even if you say I have got a very good precise sensor which is showing me 27.001 degrees Celsius, and I am uploading this data continuously, though these last numbers might be fluctuating, but what difference is gonna make? Because at the end of the day, what is your application? You want to measure a temperature. So whether you get 27.001 or 27.002, it doesn't make any difference. And temperature is not gonna vary within a second. Okay, it might vary after 2 hours, 5 hours, 10 hours. So this kind of frequency is also not desired. So many of the IoT designer make this mistake that they put lot of higher frequency than desired one. So your frequency of measurement should be optimal. It should not be less, it should not be more. Secondly, the number of bits that you store, again, that loads your computing power, and that's why again you choose number of decimal places to be more precise, or what you can say, if it is not required, just get rid of those things and just send 27 degree. So all this kind of decision you have to do at your edge, and that's why try to choose a sensor which will not have this kind of accuracy, and then you can use a 8-bit ADC which will give you a raw readings. Next is linearity. Now linearity is what you can say, if I plot a input versus output curve, and if my input varies within a certain range, let's say from 1 to 10, my output should also vary from 1 to, let's say, 10. Then we call it a perfectly linear. So this region of input versus output variation has to have some linearity. It may not be 1 to 10 with a slope of 1. It could be 1 to 5, but still it could be a completely linear region. So that slope could be 2 or slope could be 0.5. Whatever is the slope, but it should fit this equation y equal to mx plus c. Now, it is the expression, what you can say, actual measured curve of a sensor to the ideal curve. Now, let's say your measurement curve goes in this region and your actual output is changing linearly with the measured output, then you say it's a linear sensor. Next is very important factor, as I mentioned, response time. Okay. So sensor do not change the output state immediately. They need certain time. Shorter the time, better it is. Okay. So when the input parameter changes, the output parameter should also change immediately. But that is not always happening. And that's why we come to this term called response time. How fast is your output is changing? Okay. Let's say your temperature changed from 27 degrees to 39 degrees, and your sensor will slowly start showing 27, 28, 29, 30. So this is how it will gonna show the change. So there will be certain response time, and after that it will become 39 and remain stable over there. So this response time should be as small as possible. Means within a few microsecond, your sensor should able to produce the output which is corresponding to your input. So let us now discuss about different types of sensors, and I will start with the simplest sensor which is called a distance sensor. Now you have seen this kind of ultrasonic sensors. Those who are working with electronic projects, they might have seen it multiple times. They look like eye. They are basically transmitter and receiver of ultrasonic signal, and they can measure from 1 inch to up to 13. It's called HCSR04. This is the sensor model number. It has onboard crystal, everything is calibrated. It has trig and echo pin and VCC and ground. So it's a sensor module. It has a ultrasonic transmitter and ultrasonic receiver. So you can see there is T and R written over here. Now, this kind of sensor actually has two parameters. One is the range that I mentioned, and second is the angle through which it can measure the target. So there is a minimum range. Below that, there is what we call a dead band. So if object is too close, okay, let's say I have a transmitter and I have a receiver. So what happens if object is too close, that reflection will not able to reach the receiver, which is placed at certain distance. Okay. So this is where you should able to find what is the minimum range for a ultrasonic distance sensor. And this is where we call the material window for a sensor, where you can have a perfect measurement. Now, this is what I was talking about. Let's say your object is outside the solid angle of your transmitter receiver, then it will not get detected. So it's not only about this range, it's also about the solid angle of the ultrasonic sensor. Typically 65 degrees is the solid angle with this ultrasonic sensors. And if your object is not within this 65 degrees, it might get undetected from the sensor itself. Now, level measurement sensors in process control. So generally you have a flow control where you move this wall and control the flow of the liquid. Then you have a desired level which you want to measure. So as soon as you reach this desired level, either you can stop the input flow or you can release the output flow. Okay, and then there is a liquid level measurement sensor. Again, this is kind of a distance measurement sensor because it can measure a liquid level, and then based on that there will be a controller through which the decision is being taken for the output flow. Okay, so this is how a level measurement sensor is installed in a process control factory. Now, very interesting sensor because of the autonomous cars. A term is coming up, popping up multiple times. It's called LiDAR. It's a equivalent of a radar, but with a laser integrated transmission and receiver. So, like in radar, you send the microwave signals. In LiDAR, you send the visible light. Now, this can measure up to 200 meters from the position, and you can say they are a long range distance sensor. This thing rotates like 360-degree, sends the laser and measures the reflected signal back, and it's perfectly synchronized so that it gets all the data points. Now these rotating signals are powered by a wireless circuitry at the bottom, because you can imagine that you cannot have a wire and a rotating sensor. So it's completely like a secondary of a transformer installed on a top rotating part, and primary of a transformer is installed at the bottom part. And then you rotate the sensor. The important parameter to consider this sensor is when we want to measure a long distance as well as 360-degree measurement. Okay, so if you want to measure in all directions, like say I'm working on a project where I'm building a cap for the blind, I should know where are all the walls from that blind person. So this is where I am going to use a LiDAR sensor with this range. Why this range? Because then I could measure the entire scenario. So let's say my sensor range is 200 meter. That means it can measure anything up to 200 meter. So your walls are typically 10 meters apart or 5 meters. They can measure that also. Now, this is how the LiDARs are used in autonomous vehicles. And this is what we call the point cloud created with the LiDAR. Again, you will see that this point cloud is not a 3D point cloud, but it looks like a 3D because it has a depth information. So this is what we can say multi-wave LiDAR. So it has 128 scan lines. So it transmits total 128 lasers of different wavelength, and then based on each laser's reflection, it can get a reflected signal back. So it's not a single light getting transmitted, but it transmits almost 128 lights simultaneously of different wavelength, and then it measures the received signal and plots this. So this becomes the eye of an autonomous car, and then based on the obstacles, this autonomous car can drive itself. Now, very short range sensors are typically this 15 centimeter sensors. These are called obstacle sensors. Many of the times you might have seen this kind of sensors in airport, where you put your hand in front of a tap and suddenly water automatically comes. So these kind of sensors, even some of the sanitizer dispensers are using this obstacle sensors. इसमें क्या होता है, you transmit an infrared light, and then based on the obstacle detected, it receives, and then there is a comparator or signal conditioning circuit that gives a digital output. So though we call this sensor has a 15 centimeter range, basically it produces only 0 or 1, and we call them as a binary sensors. Now these sensors are very useful because now I can tune the range and I don't have to worry about the output, whether it's 15 centimeter or 14 centimeter. I will only get a 0 or a 1. So these are the easiest sensor to work with, and most of the sensor modules that give a binary outputs are very popular amongst the users. Now next is obstacle sensors. So obstacle sensors are the ones which senses the distance, like it has a colored surface and then it has a blank surface. So let's say it has a blank surface. You put the reflected light back to the sensor. You have a iron LED transmitter and a photodiode. So these kind of sensors fail if you have a transmitter or transparent surfaces, and that's where light sensors or light-based sensors fail. Now, these kind of sensors you might have seen with the student projects where they build this kind of robots, line follower robots, and they can precisely walk within certain track given to them. And based on whether zero is received to the left side or right side, the motors are moved using this driver. This is L298 driver, and then there is a Arduino board controlling the line sensor of a robot. Then there is a sharp eye sensor. So this is in between a LiDAR and what you can say a short range sensor, because this can work exactly from 15 centimeter and can go up to 115 centimeter. So this is what we call the sharp eye sensor, and this is not giving a digital output. So here you can actually measure how far is the object from the sensor. Now, again, these kind of light-based sensors do not work when we have a glass surfaces. So you should avoid any transparent object measurement using a light-based sensors. And that's why even with your autonomous cars, they do have radars also along with the LiDARs, as well as there are cameras to ensure that none of the object is missed. Okay. So here you have a ADC, typically 8 to 10 bit ADC what we use, and that is fed to this sharp eye sensor. It has a single transmitter, and a certain angle is given to the receiver. So based on what angle you receive, the output signal varies. Okay. And based on that, if you go further, your angle changes, and that's why your signal strength changes, and then you can measure the how far is this sharp eye sensor. Now coming to the very important sensor nowadays is called PIR motion sensor. बहुत बार आपने देखा होगा कि when you enter some room, light automatically turns on, and most of the times the reason is this particular sensor. If you check on the ceiling, you will see this kind of dome where as soon as person enters, it measures the passive infrared motion, and it can measure up to 80 feet or less and up to 120-degree solid angle. So again, you have to understand that it will has its own range, and this is the solid angle I am talking about. So up to 80 feet or less and up to 120-degree, this PIR sensor can work. So this is again a binary sensor. So if you just want to see there is a human or not, then you just put this sensor. Now this is passive infrared motion sensor. So it does not work with what you can say non-infrared emitting motions, like even your human body is radiating the infrared. That's why it can measure a human motion. But let's say if wind is happening and there are some plastic flaps are rotating, the PIR motion sensor will not get activated because it's not a infrared motion. So it can measure any motion of human. Even it can measure the motions from the animals. Whomsoever is a living body, even if a rat moves within that room, it will turn on the light. Okay. But if it is a plastic object and there is a wind, the PIR sensor will not able to measure the what you can say, will not get activated, and it will not turn on the light. Next is after considering so many distance sensors, we come to what we call a level sensor. Now, level sensors are the ones that can measure a level. Typically, they look like a rod and they have a groove around it so that they can fit into a boiler. And these level sensors are used for measuring the level of slurries inside a boiler or any other what you can say liquid content, and they have a kind of a short range starting from 10 centimeters and can go up to 50 centimeters of level from their position. So it's a short range sensor. You also have inductive metal sensors. Now these are the level sensors. They can measure a very small, like 1 micrometer of change, and they can measure up to 10 centimeters of level change, typically used in boilers again. especially there could be a casting where metals are there. These kind of inductive metal sensors are used to measure the liquid metal levels. So very accurate sensor, and compared to its optical counterpart, they have much larger, they may not be requiring any light to measure the level, and they can work in a complete darkness also. So typically when you consider any factory, they put optical measurement sensor and also inductive measurement sensor, and reading from both are then combined and then cross verified. If they are giving different readings, inductive one is the one which is final and not the optical one, but again they check what is the problem with the optical one, and if they are same giving same reading, then that is a final reading. So inductive metal sensors are what you can say higher preference sensor in any of the factories. Then there are photoelectric sensors. These are the sensors that used to measure the count the objects on a conveyor belt. So they have a very short range of 1 centimeter to 3.5 centimeter. They are mounted very close to a conveyor belt. Again, these are the photoelectric, so they transmit a light. So you cannot work with the transparent objects. You need to have what you can say non-transparent objects. And this is the problem with most of the photoelectric sensors. Wherever there are transparent objects, you cannot use these sensors. So while doing a selection of a sensor, check what is the type of the material that you want to count, and if it has any reflective surface, you can easily use this sensor. Next is metal sensors. Now these are the sensors which has a range from 25 millimeter and can go up to 400 centimeters. So these are the sensors which reads a ferrous material. What you can say, these are the magnets, and as soon as some ferrous material come within its range, it gives a output voltage proportional to that ferrous material. So these metal sensors are only used when you have what you can say, let's say in car industry, the body of the car do have this kind of ferrous materials, so they are used there. Also they are used in manufacturing of many what you can say equipments, where they use this ferrous material for making the body of, or you can say metallic covering of the product. Next kind of sensors we want to discuss is a moisture sensor. Now, many of the IoT applications nowadays are working towards the farmers, and one of the important things that you need in the farm is measurement of a moisture in a soil. So these kind of moisture sensors are typically having sharp points in front, so that you can put it inside the farms and inside the soil, and then it can measure the capacitive value. These can measure moisture between completely dry soil, that is 0%, to a completely wet soil, which is 100%. Okay, so these are calibrated with neutron folder, and just to have a cross calibration between moisture. Otherwise we won't able to know whether it's 100% moist soil or not. So this is how these sensors are put. You put the sensor inside next to your plant, and then this plant is saying I am happy with value of 510. So almost half of the soil is having the water level, and these moisture sensors are very useful for the farmers. So all the IoT applications related to farm do use this moisture sensor, and they produce the value between 0 to 1023, which you have to calibrate further between 0 to 100%. To do that, you just have to do a mapping. 0 will be mapped to 0 and 1023 will be mapped to 100. So if you have 512, you just divide it by 1023, and that will be giving you 50% of the moisture level. Next is the rain sensor. So rain sensors, you might have seen them onto your cars. So whenever rain starts, your wipers automatically start working, and there you use this rain sensor. Typically, these rain sensors are used to measure how much rain has happened within certain duration, and they are put into a beaker like this. You install your sensor, and then how much liquid it collects from that rain. Based on the height of the liquid, you can say how much is the rain happening. So up to 5.5 centimeter is the range of this sensor. So now if you use a bigger beaker, you can have a more rain measurement facility, and if you use a smaller beaker, that will fill faster, and if the rain is less in that region, then you can measure. So anything up to 5.5 centimeter it can measure, and within certain duration. So let's say within 1 hour, how much is the water collected inside that beaker, that we measure. Again, you see this kind of models are available everywhere. These are called signal conditioning models. They have onboard ADC, they have analog as well as digital output, they have signal conditioner, op-amp, a tuning capacitor, and any sensors you can attach to it that is varying between 0 to 5 volt. So typically variable resistor sensors are put in between those two pins, and output varies between 0 to 5 volts at the output, which you can then directly connect to a microcontroller like Arduino. Now these rain sensors could be binary type also. So if there is a complete sunlight, this is how the rain sensors reflection will go from LED to the photodiode. And as soon as rain starts falling, there will be water drop created, which will move this path, and it will not reach the photodiode, and it will activate the wiper. So these rain sensors are only used to do whether there is rain or no rain, and they can get activated even if you are washing the car. And these are the binary type of sensors. Next is a light sensor. So light sensor is used to measure the light in the room. Typical light sensors are the LDR. Again, now this is the first time we are seeing a raw sensor without any signal conditioning. So this is not a module, and it can measure any light between 0.01 lux up to 1000 lux. When there is more light, it can go up to 100 ohm, and when there is a low light, it can go up to 10 mega ohm. So you can see as the light increases, the resistance falls, and the fall is always non-linear type. So from 10 mega ohms to 100 ohm, and your light can go between 0.1 lux to 1000 lux. So these kind of curves you will always get with the data sheet of a sensor, and this is what we call the characteristic curve of a sensor. So you have to choose a sensor which has a linear region where you want to measure the where is your measurement is happening. So point of interest should be in a linear range, and please refer all the data sheets of a sensor before purchasing the sensor, because once you get it and then you realize it's not working, then you get a new one. It's not the correct approach. So always refer the datasheet of a sensor, and for that I will suggest a very good website where you get all the datasheets of all the sensors, and later on we just have a look at it maybe during the practical session. So this is how the resistance measurement unit, let's say DMM, is connected, and you put a torch on it, light falls, the resistance decreases. These kind of sensors are used in many places. In your refrigerators, when you open the door, it can turn on the light using Ldr sensors. It can be used in many applications such as protection of your vaults, or it could be also used when you open something and suddenly you want to take some action. Like in newspapers, there was Volkswagen advertisement. They use this Ldr in the newspaper itself, and as soon as somebody opens the page of the paper, the Volkswagen music started. So Ldr sensors are used typically to measure the light. One of the most common applications is whenever your sunlight goes down, you can turn on the outside lights using a LDR. Though this application seems pretty interesting, because of the many reasons they are not implemented. You will still see your municipality people will start the lights at 6 p.m. or something. They don't use this LDR sensor to turn on the street lights. The reason is dust. So in cities like Mumbai, there is a lot of dust, and if this dust accumulate on this LDR, you can imagine the light will not reach, and it can lead to all the street light on all the time. So these kind of sensors do need a lot of maintenance, since they are optically dependent, and that's why uh, you don't use them directly. Next is a important sensor which is used in many industries to measure a gas leak. It's called a gas sensor. So it can measure between 0 to 100% of whatever gas it is capable of measuring with a resolution of 0.01 degree. So these gas sensors are not the single one. They come with MQ series, MQ2, MQ3, MQ9, MQ23. There are many MQ series sensors. They all look the same. And if you want to choose the correct MQ series, you must need to know what is the gas it can sense. So many of the times LPG is the gas of choice, so that any leakage of household gas can be measured. Also, these kind of sensors are used inside a alcohol measurement. So when you travel in the night, sometimes police put this gas sensor into your mouth to check whether you are drunk or not. And there could be a binary type gas sensors. They can, let's say MQ2, whenever there is a smoke, it can produce a higher output voltage, and whenever there is no smoke, it can produce a low output voltage. So these MQ series sensors are typically used to measure the gaseous states. So different MQ series sensors are MQ8 for hydrogen coal measurement, MQ9 for carbon monoxide, MQ2 for flammable gas such as smoke, then MQ5 is for petroleum, methane, coal, then MQ135 for ammonia, MQ3B for alcohol, MQ7B for carbon monoxide. They all look the same, but you have to check their number. MQ7B for carbon monoxide, MQ4 for natural gases such as methane, MQ2 again flammable gas, MQ6 for liquid petroleum, MQ5 for liquid petroleum such as methane, and MQ6 is for isobutane, and MQ7 is for carbon monoxide. Next sensor we want to discuss about is RFID sensors. So आपने बहुत बार आपके आई कार्ड में भी इस तरह का RFID टैग रहता है, और इस तरह के कीचेन टैग होते हैं that you put near a RFID reader. What happens is energy is transferred from this primary of the RFID reader into the secondary of the card. There is a on chip that produces some digital ID, and that is returned back, and based on the logic it can give you the unique identification, typically used in attendance systems or even in shopping malls. Many of the times these IDs are attached to certain suits, so when you purchase them, it can just measure that scanners, and typical range is from 0 to 5 centimeters. So these kind of RFID, wireless RFID sensors are very useful for measurement and counting of multiple objects, and these are reusable cards. So 20 रुपए के 15 वगैरह ऐसे cards मिलते हैं, and not very costly, and you can have a lot of them, and you have to use only one time purchase of this RFID reader. Now this is how a RFID reader works. So you have your transponder tag, it has a coil inside, and as soon as it comes into the field, what happens is this field get induced, then based on that a transponder tag gets activated and returns back the signal to the receiver or RFID reader, and then based on that 00101 sequence is generated. Typically 14-bit sequence is generated, and it can go up to 24-bit RFID readers also. So you can have 2^24 itne sare objects ke unique ID, and nowadays they have also extended it up to 128-bit sensor. So you can imagine It's almost infinite cards, 2 raised to 128. So many different objects you can have. And within a one human lifetime, that is not possible to have these many objects. Next is a touch sensor. Many of the times you might have seen a lamp where you touch and lamp intensity increases, or in your malls, or just do a touch. So even in your mobile phone you have this capacitive and resistive touch, but this typical touch sensor do not have where you touch. It just say touch or no touch. So it's a binary type sensor, and it is used typically for the applications such as controlling of the lights with a touch, and how many times you touch, that you can do different action on based on that, or how fast you touch, how fast and slow, what is the frequency of touching. Based on that, these binary sensors can produce still multiple outputs. Now these are very simple sensors. When there is no touch, there is a open circuit, no flow of current, and when it touches, it actually completes the circuit, and that's why there is a flow of a current. Next is temperature sensor. So most important sensors of all time, it's the temperature sensor. Reason being, humans can't live with outside certain temperature. So you can't live in 300 degree, you can't live in 40, you can live in 40 degree, but not in 300 degree. So temperature measurement is always what you can say, an important measurement in terms of sensing. And the starting temperature sensor, I think it's based on the light. Yeah, it's called Thermopyle Sensors, and these are the sensors that can measure starting from -40 degree up to 300 degree Celsius. Next is a very common temperature sensor called DS18B20. Now this temperature sensor can measure -55 to 125 degree centigrade, and its main advantage is resolution. So it can have a resolution of 0.1 degree Celsius. Very accurate sensors, और इसकी cost सिर्फ 200 rupees है. So cost effective, and also it has one wire protocol, so doesn't take a lot of memory or wiring, signal conditioning. Everything is inside this region, and then there is a probe. So it's a probe type sensor, and this is the most commonly used sensors in many of the applications. Now you also see Rtd sensors for a boiler because of its higher temperature range. So Rtd sensors can go up to -200 to 850 degrees Celsius, and they have a metal rod. There is a different types of metal arrangement so that you can actually measure this much of temperature, and your actual sensors are then fed to the resistive measurement bridge. Then you have a K-type thermocouple. So this is a circuit for it. You attach these two wires to these 2 points, and then you start measuring at this end, and then you have your wires for connection to the microcontroller. You see this has the very high temperature measurement range. Thermocouple can measure up to 1050 degrees Celsius starting from -200 degrees Celsius. Now these kind of sensors work on a principle that you have two different types of wires such as copper and constantants, and then you connect it to the voltmeter or millivoltmeter, and you create a hot junction and a cold junction. The difference is given in terms of voltage, and basically Seebeck effect and Peltier effects are the you can say the backbone of this technology. You also have a temperature sensor which are very cheap. These are NTC type thermistors. 8 rupees is the cost, and they can measure within a room temperature like -55 to 114 degrees Celsius. Not very large value, but still a useful for what you can say room temperature measurement, and very popular one. Best part is that doesn't go bad in, let's say, 10 to 20 years is the lifetime. So Once you install a temperature sensor such as thermistor, just 8 rupees of device and it can last for 20 years. What could be better than that? Now, next is humidity plus temperature sensors. So nowadays it's the, what you can say, generation of a combo sensors. So you don't have a single sensor on your module. You try to have most of the sensors and there is a transmitter receiver chip. So this DHT11 is the most popular IoT sensor that can measure a temperature and humidity simultaneously. Temperature ranges from -40 to 125 degrees Celsius, and humidity, though it cannot measure from 0 to 100 degree, 100%, it can measure from 20 to 90%. Now inside that, you will see it has a NTC type sensor if you open this packaging, and then you have a humidity sensing component which is made up of 2 electrodes and moisture holding substrate. So this is kind of a combo sensors that are available in the market, and more the combo sensors you use, better it is for you, because less number of wirings, and it becomes easier for you to do the interfacing. Now you also have contactless temperature measurement sensor. So these sensors can have up to 35 degree, again solid angle, so within 35 degree it should be, and it can have a temperature from 40 to 85 degrees. So typically it is used to measure a high fever person. This can vary, but these are the type of the sensors that it's seen most commonly nowadays for the people. Next is because of this pandemic, this contactless temperature sensor got more value. Next sensor is a pH sensor. So pH sensor typically lies between 0 to 14 of pH, but you don't get 0 pH and neither you get 14 pH. So we generally use it for 4 to 10, but yes, the range, possible range is from 0 to 14. 4 is very acidic and 10 is very alkaline. This is the kind of setup you get with this pH sensor probe. So you just dip it into a choice of your liquid and it will directly give you the measurement, all calibrated in terms of pH. There are non-calibrated pH modules also, which comes with their own signal conditioning, but then calibration of this pH sensor becomes a really painful part. So always try to avoid any such pH measurements. Wherever you get the direct reading, always use that kind of pH sensors. Next is X-ray sensors. Now these are not very popular ones, but these are the sensors that can measure up to 33.3 lines per millimeter. These are for the short X-rays, and let's say these sensors can take a X-ray of your teeth or even X-ray of smaller parts. These kind of X-ray sensors are also used for scanning of bags, handheld X-ray sensors, and they typically has a CMOS sensor housing. Then this is the direction of a X-ray beam, and then you have your screen, a fiber optic plate, and then based on that, you don't have to throw the film every time, you can reuse it. So you have a CMOS imaging chip, and these X-ray sensors are becoming popular for screening of bags and also portable X-ray machines wherever they are required. Next is another important sensor, which is called a flow sensor. Now, flow sensors can measure from 0.3 to 6 liter per minute. What happens is liquid flows through it or air flows through it. There is a fan that rotates. Faster the flow, faster the rotation of the fan, and based on that, the voltage can be measured. So there could be a magnetic coil inside it. Based on that, you can measure the flow. So ranging from 0.3 to 6 liters per minute, this is the sensor. Yeah, this is the fan I was talking about. So more the flow, because of the structure of its wings, it rotates faster, and then there are magnets connected to this rotating part, and that produces the output voltage based on the rotor speed, and then you can have your final housing through which you can do the measurement. Or it could be a Hall effect type sensor, a magnetic sensor. So faster the rotor rotates, the more the magnetic field get induced into the Hall sensor, and based on that you can do the measurement. Now this is how the actual flow measurement is done. There is a tubing coming attached to this flow measurement sensor, and then this tubing is going out, and then you put it to the microcontroller, and then you measure this. You also apply a battery voltage to this sensor, and a very short circuit directly gives you a reading. Next is a speed sensor. These sensors are very useful in cars. They can measure up to 1609 kmph. So you know the fastest train in the world is around 840 kmph. So this is almost double of its capacity, and it can measure even starting from as low as 0.1 kmph of speed. So it has this internal ring, and then you have your transmitter receiver pair. So whenever you have a dip, your transmitter to receiver signal is received, and whenever you have a pit, the signal is not received. So you are getting a binary pulsation, and based on the frequency of that pulsation, you can see what is the speed of the car. Typically these sensors are located into the wheels, and they are mounted inside the wheels to get the speed. Two of them are used to measure the differential speed between front and back tires, and it tries to calibrate itself based on the transmission system. Next is water level sensor. So this it's similar to the moisture sensor, but this time it can measure up to 6.5 centimeter of water height, and based on how much is the water level, it can produce the different resistance, and then you can convert that resistance into the level of the water. So this is how a water level is measured. So you dip it inside a water, more the water, more lesser is the resistance, and lesser is the resistance, you can see that a level has increased. So you can set a high water level like this, and then you use a microcontroller and indicate that water level has reached certain value. You can imagine this sensor to be used in water tanks, but since it has a very short range, these are typically used as a binary values instead of measuring a particular value. As soon as water reaches this sensor and start reducing its resistance, you generate the output voltage and then turn off the motor. Next is piezoelectric sensor. Now these sensors can measure a pressure on them, and more the pressure, more is the output voltage. So that is the principle of piezoelectric sensors. So it can also act as a piezoelectric buzzers, where you apply the voltage and it generates the sound wave. But mostly now it is used for measurement between -50 to 350 picocoulomb per Newton pressures. And these are used in many applications where you want to measure a very short amount of, and very short, what you can say, pressures. This is how they are put together, and you can put a diode to correct the direction, because these piezoelectric sensors do produce a AC output voltage. So we need a full wave bridge rectifier with diodes, and then capacitive circuit to hold that voltage, and then you connect a DMM to measure the output voltage. Next is alcohol sensor. It's a kind of a gas sensor. So it's MQ3, and it's range from 0.04 mg liter to 4 mg liter. It's very useful sensor, especially to avoid drink and drive, or these kind of cases. And also the alcohol sensors are used in factories where alcohol is produced. So if you need to know the exact reaction time, these are alcohol productions are typically done using fermentation. So if you want to stop the fermentation at particular time, you use this alcohol sensors. Now this is how the alcohol sensor is attached to the microcontroller, and just 4 wires, and you get your output in mg per liter. Next is color sensor. Now this sensor can measure any color within a 10 mm of its range, and it can measure all the visible lights. So you want to copy some color, you can use this color sensor. Again, it gives a value in terms of RGB. So then you can convert this frequency of RGB into corresponding color. Typically used for paint generation machine. तो अगर आप कहीं पेंट खरीदने गए, वहां पे आप देखोगे एक मिक्सर होता है जिसमें अलग अलग पेंट लगे रहते हैं, and then they have this kind of sensor. So you show them the color that you want, and then based on the sensor reading, it mixes the basic colors. Now they don't mix RGB, they actually mix yellow and some magenta and some other color to produce any colors. And based on that, this sensor can be used for color detection. It also has 4 LED, which are white color LED, to give the luminance or perfect color measurement facility with the color sensor. Now this is the example where it is showing green color when the color sensor is placed on a mat with a green color. Next is tilt sensor. Tilt sensor is nothing but you have a ball bearing inside this, and then you have 2 rods. So whenever you tilt, this ball bearing goes away and it breaks the contact. So it's a kind of a binary system, and it can measure a tilt between 10 degree to 60 degree. So basically it does have its calibration unit. You will always see this op amp and its corresponding gain. So if you remember from your op amp circuitry, this is what you are changing. So this is what you are controlling the gain, and this is how your signal is coming to the op amp. So it's a what you can say negative feedback configuration, and this is a single powered op amp, so it only requires plus 5 volt and ground, and it also produces the output only between 0 to 5 volts. So this circuitry is always common whenever you are getting any module, and you will always see some SMD type components which are resistor bridge, and then you have your actual sensor. Now tilt sensors can also be in terms of magnetometer, so we will talk about this later. These are the MEMS sensor. They can also measure the tilt, and you can put it to the Arduino, and you can also have an ultrasonic sensor attached and make a circuit out of it. Next is clap sensor. This is not very popular, but it's a fantastic idea. You clap and let's say your fan goes off. So clap sensors, nowadays you have your Alexa, which is what you can say a more advanced version of this clap sensor. So now you have to say, Alexa, turn on the fan with a speed of 3. So Alexa can do that. But before that, they used to have a clap sensor. So you clap it once, it will turn off the fan. If it clap twice, then it will turn on the fan with speed of 2. You clap 3 times, it will turn. So up to 9 feet, you can clap. Again, it depends on how you actually clap, what is the intensity, and based on that, you can use the sensor. So you can have clap based automation of how. Next is current measurement sensor. Now these sensors are used to measure the current up to -30 to +30 ampere is the current measurement sensor range. So you just put a wire through this sensor, and it can measure what is the amount of current that is flowing through this wire. A very useful sensor, and basically it is useful for measurement of a current and selection of a fuses for the corresponding circuitry. Next is line scan camera sensor. Again, it is like a camera, but only one line is scanned at a time with a resolution of 1 cross 8K or 8129 columns, and only one line. These kind of sensors are used in scanning of multiple objects with a line scanner, barcode readers are typically used with this line scan sensors. Then comes most common sensor, CCD sensor, which is your camera, and typically it has 45K capacitors in your one CCD sensor, and you can see so many pins. It has a array, so not 45K pins, but it's a root of 45K. And typically these CMOS and CCD sensors are used for the capturing of the images. So you can see that both has its own advantages. CMOS can do a parallel measurement where CCD has to do a serial measurement. Accuracy or clarity wise, CCD sensors are more better compared to the CMOS sensors. And nowadays, every mobile phone is going for CMOS based sensors, compensating on the clarity. And your DSLR cameras or some of the high-end movie making cameras are still sticking to the CCD sensors. CCD sensors are slow and they take a lot of space also, and that's why they are able to capture more light, and they both have its own advantages and disadvantage. So if given a choice, nowadays CMOS sensors are more preferred over CCD because of the cost effectiveness. Next is depth sensing camera sensor. So this is a very novel sensors. It uses a infrared projector, low res RGB cameras, low res infrared camera, and typically two RGB sensors spaced at a distance of eye, so 6 to 7 centimeters, and they actually perceive the depth along with the actual object. So this depth camera can measure a depth between 1 to 120 meters. Because of the silicon shortage, these cameras are not available right now, but soon they will be in the market, and they are very useful sensors to measure the depth in an image. So you generally have only RGB with your images, but this depth camera do give you RGBD, and the D stands for the depth. So this is our depth camera's D plot looks like. So closer objects are in blue and further objects are in red, and in between there is yellow. So this is how the depth camera gives the readings. Radiation sensor is the one that used to measure the radiation between 0 to 100%. These sensors are typically used near atomic reactor centers. So it measures the incidence ionizing radiation. So very high voltage is present between the probe and outside neutral, and based on the type of the radiation, it can give you the reading. Then you have your solid state radiation sensors also available in the market with a sensitivity of almost 3.4%. So these radiation sensors are used near what you can say gamma radiation. So you know there are three types of radiation. So we have to protect ourselves from all different types of radiation. Especially the atomic reactor facility do need these kind of sensors. Then you have your pressure sensors. These are typically 0.36 to 1 psi sensors, and they can be attached to the boiler, and they can allow you to measure the pressure. So typically two pressure sensors are mounted, one in the top region where there is a compressed air, and one at the bottom where there is a liquid, and based on the readings your computer can take up appropriate action onto the boiler. Now in the start of the talk I talked about a mall door. So this is the sensor, microwave sensor, which is used at those doors. So initially I thought it was a PIR sensor, but later on I realized PIR sensors cannot be used in that door sensor. So microwave sensor is what we actually use in these mall doors. It may not be mall, it could be any shopping complex where you just stand up and the doors automatically open between 2 to 16 meters if anybody moves in that region. these microwave sensors are used. Even to have a entire railway mapping, these microwave sensors are only used. So which train is passing through which station, that is achieved through this microwave sensors, and these are placed at every 300 to 30 kilometers range, so that each train can be tracked down. So these are very similar to what you can say your PIR sensor. Only difference is now it can measure the metals, whereas PIR sensors can only measure infrared heat. Microwave sensor can measure any object, any moving object, and it can also produce binary decisions also. Next is vibration sensor. Again, it has a ball bearing inside and two rods attached to that ball bearing. So what happens is if you vibrate this sensor, this ball bearing jumps up and down, and it just disconnects the contact and connect back. So you get a square wave pulsation at the output, and based on the frequency, you can measure the vibration. There is no change in amplitude. So typically this vibration sensor can produce 100 millivolt per G, and used with motors or any vibrating instrument where the vibration is important to measure, and you have to mount them against gravity. So this thing always points towards sky. So this is how accelerometer can also be used to measure the vibration. Put accelerometer on top of your machine, and it can give you the acceleration data. Now next is particle sensor. These are the sensors that can measure a particle up to 0.3 micrometers. So basically these sensors are used in clean rooms where you want to measure particulate count, or also in the air quality systems where you want to see whether the air is breathable or not. Now we heard a lot of things about Delhi air pollution. So there a particulate sensor with IoT device, a complete deployment is needed. Next is oximeter sensor. These are max 30100 oximetry sensor. Because of this pandemic, measuring pulse oxygen is very important. If your pulse oxygen level drops below 93, you should always check the doctor whether it's a corona or not. So pulse oxygen measurement has become an important role, and this can measure between 70 to 100% of your pulse oxygen level with 1 or 2% accuracy. Now this circuit has 30102 is what you should use always, because Chinese manufacturer Max 30100 has produced a wrong sensor and deployed almost 1 lakh unit of this Max 30100 in the market during the pandemic. Everybody is purchasing and this sensor is not working because one slight track mistake, the sensor is not working. And if you are going to the market, always use Max 30102 instead of 100. Now the pulse oximeter can have a transmission and reflectance mode. So photodiode is connected on the same side. Your LED and infrared both are just feeding back the sensor. So this is a Max 30100 type, or your LED and infrared light are opposite to the photodiode. This is what you see in pulse oximeters. Then there is a flame sensor. So flame sensors can sense flame within a range of 760 nanometer to 1100 nanometer wavelength. These are nothing but a receiver of IR, infrared receivers, and they can sense any flame. So this is how a flame sensor is placed over here. There is a light or flame, and then it is fed to your Arduino, and based on that there is a buzzer that can ring and detect there is a flame. Next is Lvdt, a very common distance measurement sensor, but it can measure within 100 micrometers. So very small moment, and up to 25 centimeter it can measure. These are nothing but a complete sealed sensors where this rod move and this rod motion is tracked down. So this is how Lvdt is mount with a generally drill press unit, and how much you are drilling, you can measure that. based on the Lvdt measurement sensor. Then you have your fingerprint sensors. So fingerprint sensors you might have seen in your offices where you put your finger and it has a resolution of 500 dpi with 0.1% rejection, false rejection. So your finger always have valleys and ridges, and based on that you can measure the finger's position or person's finger. And this sensor is a capacitive type sensor. Next, we come to the actual IoT sensors. So Internet of Things are nothing but sensors that are connected to internet. So you have your smart rings, smart watches, smart shirt. You also have your Bluetooth key tracker. Smart shoes are there, smart socks, smart pants, smart belts. Even you have baby control. You have smart bracelet and nowadays smart fingers. So many smart things are coming up. Now these smart things are nothing but a sensor with a Wi-Fi connectivity. That's it. Then you called it a smart thing. So ideal desired IoT sensor should have a small size. It should be inexpensive. It should be energy efficient because this IoT will not have a lot of battery. They should be up to date to the technology and there should be a repeatability in the measurements. So let us understand what are those typical MEMS based IoT sensors. First one is MEMS gyroscope that can measure angular velocity starting from 30 degree per second and can go up to 4000 degree per second. These are the internal structures which are very small rectangles and some pins at the back. So MEMS sensors all has this kind of structure. They do not reveal what is the technology inside those sensors, and they just have small packages like ICs, but they do all the measurements. Then you have a MEMS accelerometer that can measure up to 40 G forces. Again, it has a lot of pins outside and you can see a lot of MEMS suspended mass inside, so that acceleration can be measured in XYZ direction. Now you have a combined accelerometer gyroscope sensor. They are called IMU sensors. So they can do a inertial measurement unit, IMU, and they can do accelerometer, gyroscope, barometer, everything is inside a single sensor. Then you have MEMS pressure sensor that can measure from 2.5 to 30 psi, and its size is not more than 2 centimeters. So all these MEMS sensors are really small. They could be only half centimeter by half centimeter and can as big as only 2 centimeter by 2 centimeters. Then you have your MEMS microphone. Again, minus 120 to minus 140 dB sound pressure level it can measure. And if you open them up, this is what you will see inside. Then you have your MEMS humidity and temperature sensor equivalent to your DHT11. This can measure from minus 80 to 120 degrees Celsius, and humidity can be measured from 0 to 100 degree. Then you have your MEMS gas sensors that can measure from 0 to 1000 ppm. Alcohol can be measured with 10 to 500 ppm. Then you have advanced system made with this MEMS sensor. You have already seen virtual reality headsets. So based on way you move your head, the Samsung Gear VR can track down the motion and fade back to the mobile. So all these sensors, MEMS sensors are inside your mobile phone. So next time, whenever you sell your mobile phone at 500 rupees as a resale value, please understand that there are a lot of hardware going to Bhangar, what you can say. So soon there will be a lot of need to convert this e-waste into something useful, because the thing that you are selling for 500 is having more value to it, and somebody needs to understand and you reuse those stuff inside, because only battery or screen will go bad. Rest of the stuff is still having a lifetime of almost 10 to 20 years. Then nowadays there are smart wearable sensors. So You have your sweat biosensors or signal processing unit that you mount on your shirts, and all the energy is automatically harvested. And then you mount your mobile phone or connect these sensors to via Bluetooth to mobile, and then you can send it to internet to have your health status measurement done. So to summarize this talk, selection of sensor criteria depends on a range. Okay, so what range you can measure, very important parameter. Then resolution, what is the lowest resolution up to which you can measure. Next is sensitivity, what is the sensitivity of your measurement. Next is error, what is possible error. Then you have accuracy, how accurate is your sensor. Then precision, how repeatable is your sensor reading. Response time, how fast your sensor can respond. Signal to noise ratio, so is your sensor responding to outside noise, or does it only respond to your signal. Then calibration, do your sensor require any calibration or not. Then cost of a sensor. Then nature of the output, whether it's analog or digital. Environment in which your sensor can work. Flexibility, like this sensor can be used in many application or not. Interfacing, like which protocol does it support. Does it support I2C? Does it support regular serial? Does it support one wire protocol? And then finally size and weight, whether it's a MEMS based sensor or whether it's a bigger sensor made for larger applications like boiler, etc. Whether the sensor is useful directly to the PLCs between 0 to 24 volt, or is it made to be used for microcontrollers between 0 to 5 volts. All this stuff does contribute to a selection criteria for the sensors. I think with that, I end my talk. And if you have any doubts or questions, I will be happy to answer them.
Sir, I have one doubt.
Yeah.
You just mentioned about MEMS sensors now.
Yeah.
So what are the points, major points which make MEMS sensors dominant over the normal sensors?
Okay, so firstly, these MEMS sensors are smaller in size. So smaller size means less power consumption, and that's make it ideal for your IoT applications where battery size is very limited. So let's say your battery is 33 milliampere hour and you want to run your measurement unit full for full day. It cannot consume more than 1 microampere per minute hours. So based on that, MEMS sensors are always preferred. Cost wise, sometimes MEMS sensors are costly compared to the regular sensors. But again, at the end of the day, if it is a IoT application, I would always prefer a MEMS sensor over a regular sensor. Secondly, it is very difficult to solder these MEMS sensors. So the kind of technology we have in India, we are not very SMD friendly. So that's why these regular sensors are sometimes preferred if you are just a beginner. But if you have advanced soldering facility, always go for MEMS sensor.
Okay, sir. Thank you. Sir,
Yeah.
one more question.
Yeah.
You said about RFID tags, which are observed in many of the malls, shopping malls,
Yes,
which are
yes.
fixed with all the items.
Yeah.
But sometimes it happens like it is not removed by the person who is billing at the billing counter.
Yes, yes.
And when the person exits, some buzzer or alarm is ringing there.
Huh.
So can you explain what happens exactly there?
So there are two types of tags that is put into the malls. One is mandatory removal magnetic tag, which is connected to the coat. And if you see at the billing counter, whenever they bill, they remove this tag. This tag is only to ensure that nobody is taking out the clothes without knowledge. These are bigger in size and gray colored. They require a very powerful magnet to detach from the object. And the other kind of tags are sticker type. They only have antennas and one chip. They are like stickers only. And sometimes as soon as billing is done, this sticker is thrown out of the system. So ideally, if it is billed, even that sticker remains onto your object, it should not ring the alarm. But if the bigger tag is not removed by mistake, then it might create a problem. The sticker type tags are generally for build items, they remove from the system. So even when person take it out of the mall, it is fine.
Okay, sir. Thank you.
Good morning, sir.
Yeah.
I am Professor Shelgaonkar from AP Shah Institute of Technology.
Yes, sir.
Yes, your session is very comprehensive. I would like to know which sensor do we prefer for the phototherapy unit in maternity hospital, because the blue light radiations which are generated and that are useful for the to cure the jaundice of neonatal.
Yeah. So typically these ultrasonic the light measurement sensors are used for the ICUs, baby ICUs. And these light sensors are covered with a special type of filters.
Okay.
And this UV therapy is basically measurement of UV light. And what we do is put a UV filter on top of a LDR, and then we measure the reading. So
okay. And is there any for the measurement of wavelength or that we have to consider?
Yeah, so wavelength is taken care by that filter.
Okay.
So the light filter itself is set to the wavelength of a desired UV.
Okay. Thank you, sir.
Yeah.
So there are few questions in the chat box.
Okay.
What is basic difference between transducer and sensor?
Okay, so transducer is one which has capability of working on its own. So what you can say, they do not require any external power supply to work. Transducers can be self-powered themselves, and they directly produces the voltage, whereas sensors typically gives output in terms of resistance variation and maybe capacitance variations, which further needs signal conditioning to give the final results.
Okay. This Deepali Patil has asked one question. Can you provide any website link for datasheets of sensor?
Yeah. Maybe in my next session, hands-on session, I will give you the entire detail of that.
Okay. Professor A.A. Syed has asked, what are the different selection criteria for the sensors?
Okay, so I think my last slide was based on that. So only main criteria is range. So if you, based on the range, you can select the sensor, and then you can, based on the cost, you can decide all other parameters. But it has to be a perfect range. So this is the selection criteria slide. All 15 parameters you can always consider before buying a sensor, and based on the cost, you decide for the other parameters. But range has to be considered. So throughout my slides, I just talk about range, and only few slides I just talk about resolution. But other parameters are always dependent on cost of a sensor.
Yes, participants, any other questions? I think no. Such a wonderful session. You started from basic concept of sensor to real life applications for vast variety of sensors, and also mentioned the selection criteria for the sensors. So thank you, sir, for sharing this valuable information with us. A gentle reminder to fill the attendance cum feedback form. The link is shared in the chat box. Link will be active for next 1 hour. Now we'll have a lunch break for 1 hour. So we'll all meet at sharp 1 o'clock. Thank you.
Okay, bye.